Okay, in part 3, our next rational function is going to have a hole in it. So this is example 4. The rational function this time is the quantity x squared plus 4x minus 5 over the quantity x squared plus x minus 2. Again, the first thing I'll do is factor everything. Just makes my work a lot easier. So the numerator factors into x plus 5 and x minus 1. The denominator factors into x plus 2 and x minus 1. What we're going to notice is that both the numerator and the denominator have a factor of x minus 1. It is a fraction. That means you can cancel things out that are alike. Now, we have to remember that, right? So we cancel that out. I'm going to make myself a little note. X equal 1 is a problem. So in other words, if I plug 1 into the original function, I'm going to end up dividing by 0, and we can't divide by 0. So we'll worry about that at the end. The steps themselves are the same. What we're really graphing is we're going to come in and graph this. So I'm ignoring the original function. I'm working off of the reduced fraction or the reduced function. So our x-intercepts coming from the numerator again, that would be -5. Our y-intercept, if I let all the x's be zeros, and I end up with 5 over 2, so that would be 0, 5 halves. The vertical asymptotes coming from the denominator. At -2, we have issues. The horizontal asymptote, we come in and look at the degrees. So the degree at the top is 1, degree in the denominator is 1. So again, degree numerator is 1. The degree of the denominator is also 1. So they're equal. So that means it's the ratio of the coefficients. So in our case, the coefficients are 1 over 1. So 1 over 1, not the degrees of 1, but the coefficients of 1, which is y equal to 1. So there's all the information. Let's go plot it. Okay, so we have -5, 1, 2, 3, 4, 5. We have positive 5 halves, which is 2.5. I have a line at -2 that's a vertical line. There's x equal -2, and I also have y equal to 1. Looks something like that. Okay, let's draw it in. Again, if we have a left side, we have a right side. We pretty much know what's going on because of those points. So on the left side, there is an x-intercept I need to pass through. So we're going to come in and go through that point. So start right below the horizontal, pass through the x-intercept, head towards the vertical asymptote. On the right-hand side, we know it's got to pass through that y-intercept. We've got to start by the vertical asymptote. Again, it cannot come up from the bottom because it would have to cross the x-axis to get to that point, and there's no point over there on the x-axis. So there's no intercept. I know it can't come from the bottom. I also know that because the multiplicities, both of the multiplicities for all these factors are 1, so we're going to alternate regions. So if it's below over here, it's above over here. Going to head towards that y-intercept and then head towards the horizontal asymptote. And there's our graph so far. Looks very similar to the one we graphed the very first time, and it should because it was a linear factor over a linear factor, so it makes sense. But now we have to address our problem with our hole, right? So we're going to recognize that in the original function, x cannot be a 1. So wherever x is a 1 on your picture, you're going to go directly up to the graph itself, and you're going to make a hole. And there's the graph of the hole. So it is discontinuous on this piece because there's a hole sitting there at x equal to 1. And that's how you graph a function that has a hole. So the hole gets addressed at the end, which is nice. Okay, 2 more examples. What we're going to do next is start with the rational function and then write the picture or the function that goes with the rational function. So this is example 5. So example 5 says, let's find the rational function that might have the given graph. And we saw this graph before. We saw it in the previous section. In that section, they just asked us to pull the information from the picture. Comes in, so this is at -2, this is at +2, this. Notice it is bouncing at that x-intercept, very, very important. And then we have a horizontal asymptote up here at 1, it's above, and it's above. Okay, so there is a picture. Let's see if we can write the function. So we're going to take the information and put it back into the equation. So R of x, I like to use R because it stands for rational function. Okay, well, we know that the vertical asymptotes come from the denominator. So if they're at -2 and +2 from factors, that would be x plus 2 and x minus 2. The numerator is the x-intercept. Well, the x-intercept is at the origin and it bounced. So I know that I have just an x and I know I'm going to square it because of the bounce. So I'm going to have an x squared sitting in the numerator. So right now we have x squared over x squared minus 4 if I were to multiply it out. You don't necessarily need to, but okay, now we're going to check. So we already know the x-intercept is fine. We already know the asymptotes are fine. Let's check to make sure everything else works. So does it give me the correct horizontal asymptote? Well, the horizontal asymptote's got to be at 1. When I look, the degrees are equal. They're both squares. So it's the ratio of the coefficients. Well, the coefficients are 1 over 1, which would give me a horizontal asymptote at 1. Perfect. What about the y-intercept? Well, if we let all the x's be zeros, I end up with 0 over a -4, which is 0. Sure enough, it works too. And there's our rational function. You don't really need the ones there, but that's the rational function. So it's actually a lot easier to go from where we're at the end back. If you ask me. Okay, one more example, and we'll call it good. So the next example is a real life application problem of a rational function. So this is example 6. Example 6 says the concentration C of a certain drug in a patient's bloodstream T hours after injection is given by C of T is equal to T all over 2T squared plus 1. So T is in hours and C of T is the amount of drug in the system. So drug in bloodstream. Okay, what they're asking us is to find the horizontal asymptote and what happens to the concentration of the drug as time increases. So what does that horizontal asymptote mean in the real world? Well, so we're going to come in and do our analysis. To find the horizontal asymptote, we look at the degree. The degree of the numerator is 1. The degree of the denominator is 2. So it's bottom heavy. And anytime it's bottom heavy, I know it's the line y equal to 0. So it's the x-axis. Okay, so what we're graphing is time and concentration. So what we're saying is way out here at infinity, this graph is coming in and doing this. So the dotted line is sitting right along with it. So our horizontal asymptote would be the line C of T equal to 0 or C equal to 0. And what this is simply saying is that as time increases, the amount of drug in bloodstream goes to 0. So as T increases without bound, then the concentration is going towards 0, which makes sense. The drug is wearing off. So a lot of drug concentration problems are applications of rational functions. And that wraps up our rational functions. We have one more section in chapter 5. That's the polynomial and rational inequalities. And that's up next in section 5.4.